Okay, so good morning, and so today we will continue our study of functionals and their derivatives. And after about a quarter of the lecture, we will move on to its application in classical mechanics. We already saw how it connects up with classical mechanics in one simple example, that is Newtonian mechanics, and we will continue to extend those considerations and see how to proceed. Okay, so last time we were looking at functionals of one variable. Okay, and so we defined. So the idea was that q and q plus delta q are two different trajectories. Trajectory, two different functions. Such that q of 0 equal to 0. So these are kept fixed. So the delta q of 0 should be 0. Similarly, at the other end point, we are looking at functions whose endpoints don't change. They are fixed to some values. And so we defined the functional derivative by studying Taylor series. So this was, if you wish, the definition of the functional derivative, and we saw how to compute this in several examples in class as well as the tutorial, problem sheet 2 or 3 rather. Okay, so first thing we'll consider is what so instead of so we'll consider functional in many variables. Okay, so what I have in mind is something like this: q1 of t, q2 of t, q3 of t, so on and so forth. So I'll write it in short as f of some index qa of t. So a can go from 1 to 3 up to whatever degrees of freedom that we have. So let's say it has n of them. So this is still, it has independent functions, but now qa at 0 and qa at t are fixed. Okay, so now when we do the variation of this function and we want to write a formula which is the generalization of this, which is like the generalization of Taylor series in many variables. So recall. So we'll take function and I'll use x for that, and a again the same index is run from 1 to. Okay, so So there are n independent directions, and each one of them is characterized by a partial derivative with respect to variable xa. So just direct analogy with this, we can write. So if something is unclear, please ask me, because I cannot see what is written in the chat box. Is this clear? So there will be as many derivatives. So we don't have a special symbol for functional derivative, but this is functional derivative with respect to q1, q2, q3 up to qn. So this is the analog of partial derivative. So this is what one will write. Okay. So I'll just do one example of how to. So let us say that f. So example. So suppose we have this functional I of t naught, qa, to be say q3 evaluated at time t naught. Okay, so then delta I t naught to work this out will be delta b3 chronicle delta. Okay, so this appeared in our example. We have seen how this. But now the fact that there are multiple fields shows up in this chronicle delta. Is this clear?
Sir, why is it specifically b comma 3?
Because my functional is picking out q3. I chose it to be that way. It has to do with the functional. If you had chosen q4, it would have been delta b4. If you have written some qc, it would have been delta bc. C is some variable.
And b is just like t minus t naught. It is so it's basically
Yeah, it
b
is
minus
this.
3.
Yeah.
Okay.
Well, it is not b minus 3, but yeah, it's delta b comma 3 because it's a discrete delta function. The other one, but I know I know where you're coming from, and yeah, morally what you're saying is correct. Okay.
Okay, sir.
Any other questions? Okay. So I want to do one more extension. Okay, so second order. So let's do it again for function of one variable. Generalization to higher variables is easy. Zeroth order term, first order term, okay. So this is clear, right? This is just standard stuff. You can write in some ways, actually, I feel that I should have chosen the example with many more variables, and then we'd have seen a little bit more structure. But that's okay. It doesn't matter. I started with something, so let's just do that. So I'm going to write exactly the same thing for my functions. Okay. So notice that there are two integrals, not one. Okay. And so my comment earlier was that I should have written it with respect to many variables. Then you would have seen that in the linear term there would have been one summation. In this thing there would have been two summations. Okay. So xa, xb, so summation over a, summation over b. But here there would have been only summation over a. Okay, like we saw here. So, is there anybody who needs a little bit of so you can see that the object that we have defined here, so the remark here, the second functional derivative is a function of is a function of two times. Okay, so we write it like we write it one more time. Okay, so this is something. Okay. Okay. So exercise would be compute the second derivative.
So for
Yeah, go ahead.
second order Taylor series, was it second order but still one variable?
Yeah, it's still second order in one variable. Yeah. So if there are more variables, we would have just put something like this. The generalization is so easy for more variables, so I'll just write it here. And you would sum over A and sum over B also.
Okay.
Okay. So exercise is to compute the second derivative. Do one example. Let's do one example. So f of q. Yeah, this was what I called f1. I think. Let me see what I've written. Yeah, I call this f1. Okay. So you just go ahead and ask what this thing is. Okay. So I won't do this computation. Maybe we can push it to the tutorial, or you can ask me a question next time. Okay, so just another historical remark is in the context of calculus. Another remark: the Kerala School of Mathematics, okay, knew about second order variations. I mean, they derived it over years, like about second order Taylor series. Taylor series to second order. I should not say second order Taylor series. Knew about Taylor series to second order. Okay, so since they were interested in astronomy, not astrology, astronomy, okay, they focused on trigonometric functions, such as the sine theta, the sine theta. Okay, so so the point is that they needed these things to arbitrary precision. So what they would do is break up 2 pi into some bunch of intervals, and they need to compute sine of, say, 2 pi n by n. All these values, they would tabulate them, and they have to make them, they have to compute them to some accuracy. And they knew about Taylor series. It's a simple statement, and they implicitly used that. And you appreciate that this was done before calculus. I mean, well before Newton. So it's just something. So I kind of like the fact that a lot of things we do in physics can be understood if you understand up to Taylor series up to second order. I mean, so first order will give equations of motion. Second order will tell you about stability in classical mechanics. Okay, so so now we will go to classical mechanics. Okay, so we saw that Newtonian mechanics can be understood from maximizing a functional, okay, for the action, and so the action functional was a function of, I'll write the general case. It's a function so the input is something called the Lagrangian. So in principle there could also be explicit time dependence, but in Newtonian mechanics there was no, in our example we saw that. So we will generalize that. So where L of t uh, took the form of t minus v, where t, the Cartesian, was just half n x dot square plus y dot square. So qa, so I'm just saying q1 is x, q2 is y, and q3 is z. Okay, Cartesian. We know how to handle v of x, y, and z. Okay, so extremizing, so delta S by delta Ui of t will be equal to, sorry, let me skip, I must have writing something. And this is nothing but n. So this is what we had worked out. Okay, so this is just standard. So ideas, so the idea going back to, Euler, Lagrange, and others was to say that generalize this, say to choose pick some action. So the methodology is as follows. So let's do step one is identify the coordinates, the degrees of freedom actually. Okay, and they're called generalized coordinates because they need not have dimensions of length. For instance, it could be anything. Okay. Step two is write an action. Okay, so even allow for time dependence. Okay. So the cleverness goes into this is the Lagrangian. So all the dynamics refers to time evolution is obtained given the Lagrange. So and the equation of motion becomes, so this is something which we saw last time. dl by dx minus this was an exercise in your thing, even whether this is time dependent or not, it doesn't matter. This is what it is. This is the thing, and there are n equations. So a equal to 1, 2, 1, n. Okay, so so the point is that the Lagrangian is a function of q dot and this. Yeah, go ahead.
So while writing Newton's equation, the necessity is that we should work from inertial frame of references. So is there the same necessity for writing down the Lagrangian?
What is it? Same? What frame of reference?
I mean, while writing Newton's laws, we must work from inertial frame of references. So while writing the Lagrangian, does it require that we must be in a inertial
We'll put
frame
it.
of
Yeah.
reference?
So that's actually a very nice question, and so I will discuss that how to. So that goes into how you choose a Lagrangian, how where how this would happen, how you would go about choosing a Lagrangian. Okay, so there will be some constraints we'll put on the choice of Lagrangian. So this is step 2, where we have to write an action function, and so you have to put in some ingredients, and we will see how how to choose some things. Okay, we'll see that it will give you some conditions. So it will put restrictions on the Lagrangian. This is what it will do. So, for instance, if you say that your space is isotropic, that means there is no preferred direction. Okay, then it will tell you that this thing has to be a scalar function under rotations and things like that. Okay, so we will see that. We will see. I mean, very
Sir,
yeah.
sir, how was the action integral chosen? Means how it was proven that the action integral would lead to Newton's law? Means how that function was chosen, that Lagrangian.
No, they knew Newton's laws already. So I mean,
It was from Newton's law. It was.
So but the point is that the key observation is that Newton's equations arises from generalizing an action functional, but the action functional is much more general than Newton's laws. I can choose actions which are more general than Newton's laws. I mean, do something beyond Newton's laws. That is a key point. So this is where so this is what these guys did, Euler, Lagrange, etc. Okay, so these equations we call them, at least paying homage to them, these are called the Euler Lagrange equations of motion. Okay, so this is how we pay tribute to these guys, who realize that they have a setting which is much more general than Newton's equations. Okay, Newton's equations is based on something mechanical. Okay, so for instance, Maxwell's equations is not mechanical. Right? I mean, so yeah, so let's do this remark. Very important question that you guys asked. Newton's equations are a special case. Okay, so there are systems which are non-mechanical. I mean, like electromagnetism, which also fit into this Lagrangian framework. It's much more complex. complicated than this, but from the viewpoint of making the statement, I mean, it's that's what it is. Okay, so there are some nice things which come. Okay, so the generally one obtains an equation of motion. POM is equation of motion. That is second. That has the second derivatives. Okay, why is that? It's easy to see. So if you look at the Euler equation of motion, this guy, can you see my mouse?
No, sir.
Now?
Yeah, we can see.
Now now, okay, good. So this term, of course, is only does not have is a function of q and q dot. When we take derivative with respect to qa, it remains only a function of q and q dot. But here, this fellow inside the braces or brackets, this is a function of q and q dot. But now we have a derivative coming here, so you can get q double dot. Only one occurrence of q double dot can come. So these are in general second order equations of motion. So we have to integrate it twice. So in that sense, it is like Newton's equations. Okay, and these equations, I forgot to say, we have to give QA at 0 and QA at t have to be specified. Okay, that's the general thing in we know from this functional calculus which we did. Okay, so this is generally okay. So in that sense, it is similar. Okay, so you have to do two integration, but okay. So and we need to do two integrations. Per variable, of course, to obtain the trajectory. Okay, but there are a couple of instances where there is a simplification. Okay, so let us look at both of them. The first thing is L, the Lagrangian, is independent. So okay, so I'll stick to just one dimensional. Okay, so then what does this mean? It means dl. What can we say about dl by dq?
0.
It is 0. Okay. What happens to the equation of motion? The equation of motion becomes very simple. It says d. So it becomes very simple, and we can do one integration easily. Okay, so let p be defined to be this quantity dl by dq dot. Okay, this has a name which I'll write out now, called the generalized momentum. Characterized as a generalized coordinate cube. So it's called, given, and reason it's called momentum is because in Newtonian mechanics this will be exactly the momentum. Okay, for Cartesian coordinate. Okay, so it's just borrowed from there, but generalized momentum again. So this equation, integrating once, so you can write this E, which is we saw defined to be dl by dq dot equal to. Okay, so this is what follows. So if you have many variables, say q1, 2, q3, q4 up to qn, and suppose the Lagrangian is independent of only q4, okay, then there are many equations, but one of the equations will involve p4, which is dl by dq dot 4. That will be a constant. That generalized momentum conjugate to q4 will be constant. So you can see that sometimes we get lucky, some simplifications happen. So this is this clear what is happening? Okay, so one term. So second example. I'll pause. Are there any questions, comments?
We need to vary the initial and final conditions, like population, and the final cut.
Can't hear you. Can you type it? Probably better. Type in the chat. Okay, so I'll wait for somebody to type on the chat. Meanwhile, I'll just move on to the next example. Okay, next example is when so what does that mean? It says that the partial derivative of L with respect to t is 0. Okay, this is, you agree with this? This is just standard. It's L is a function of q dot and t, and it's independent of t, so that's the partial derivative of 0. So let us see what does this mean. What does this give us? Okay, so then let us do this. Let us consider the total derivative of L with respect to t. So this is the partial derivative. This function in 3 variables, dl by dq times the variation of that, so it will be q dot plus d by dt of q dot, which is q double dot, plus this is just a formula from multivariable calculus. Right? It's a function of 3 variables. Each of them I can vary, and that's it. Is this clear? Okay. So, but we can do a little bit more. We can let me do the following. I have q double dot, so what I'll do is I'll integrate. I write this follows. Yes. I can integrate by parts and take this. What do I want to do? Yeah. So I've just taken this term and written it as two terms. Okay, so now we can see that I can collect terms. I can look at this and this. Okay, so you can see it's q dot times and write that here. Okay, yeah. No, what am I writing? Sorry. Okay, so this is just this thing. So now we can see this. What can we say about this term? Which I have, that is zero using equation of motion. Euler-Lagrange equation of motion, right? And this is zero. Why is this zero?
Time independent.
Exactly. Okay, so this is dl by dt equal to, this sign is wrong, this is plus. Okay, so this can be, so now what I get is, I can rewrite this whole thing as d by dt of p q dot minus L equal to 0. Okay, and so this quantity is 0, which implies that pq dot minus L is a constant, which we will call p. Okay, this is a constant of integration. This is okay. So the quantity combination p q dot minus L, okay, is the energy, and p, what is p? P is just dl by dq dot. Okay, so this is what we do. So again, what is happening here is that one integration can be done. Okay, so you can see that every term on the left hand side is only a function of q dot. Okay, so one integration. Okay, so exercise, show that for many variables You get, one gets. This is what you get. Okay, and I use the symbol E because for simple examples, this becomes the energy. Okay. So
Hello,
now I can,
sir.
yes.
E is a function, right? It's not
E
a
is
number.
not a function, E is a number. It's a
But
constant
sir,
of integration, which is determined by your initial condition.
okay, sir.
By
L
boundary
is Lagrangian is a function of Q and Q dot.
Yes.
So left hand side we have Lagrangian. P and
Yeah,
Q dot
left
themselves
hand
can
side
be
is a
function of Q and Q
function.
dot.
Left hand side is a function of Q and Q dot. Yes. And that funny combination, the motion is going to be such that that particular combination will be a constant. Okay, so it's like saying energy is a constant of motion. So E,
Okay.
that's a constant of motion. Okay, so let me read this question from Rahul, Sai Rahul. In calculating the Lagrangian, we need the initial and final condition. So we are not really doing. Oh, we are. So okay. So Rahul has an interesting question. So let me draw a picture. So let's say this is Q and T, and this is 0. Let's say this is T, and let's say that you are given these two values. Okay. So you're given these two values, you don't know anything, right? Well, it's not. I mean, so what I mean by giving time evolution is to give the curve, precise curve, which solves the equation of motion. So you have to give me this curve. This is curve. This is not given to you. There are infinite number of curves which will connect Q of 0 with Q of T. These two values are fixed. I mean, I can have something else which. So we have to determine this thing. So we need to get the trajectory. So we don't know that. Okay, so we have to give. You have to tell me how it evolves in time, right? How it goes from 0. We know it starts from here and goes here. Okay, but we don't know how it goes. So that's why it's called giving the time evolution or the dynamics. Okay. If you knew this, then there's nothing. There's no computation needed, right? Okay. So you get. Go ahead.
So in Newton's laws, we pose the problem as given initial conditions and given the Newton's laws, you have to work out.
No. So this is not that framework. Okay, we'll see something called the Hamiltonian framework, where we give initial conditions and let it evolve in time. Okay, so that's a different thing, and we will see that there is an equivalence between these two laws.
What I mean to ask is that defining the problem as a boundary condition problem is equivalent to the Newton's laws. I mean, that's what I'm going to ask.
Yeah, that's what we will see. Almost true.
Okay, thank you.
Okay, yeah. So see, Newton's laws, the way we usually solve it is like an initial value problem. You give me at t equal to 0, you give me q and q dot. You have to give me two numbers. Here, what we are saying is to give q of 0. You're also giving two numbers here also, q of 0 and q of t. You're not. That doesn't determine for you, for instance, q dot at 0. We don't know q dot at 0. Okay, so how do we know it's going to touch q of t? Because we are only looking at the space of curves which start at q of 0 and start of t. So we are in that space. So that's all we will get. Okay, so to show so we will that is a few lectures down the road, we will show that we can convert this problem into a different problem, which is the Hamiltonian problem. Okay, which is in a set of different variables, and we'll see there is something called the Legendre transform which relates these two formulations. Okay,
so we will convert this boundary value problem as the initial value problem, right?
Yes.
Thank you.
Okay, yeah. So you can see that these two. So we have two such examples, and so let us now. Do I have time? No, I don't have time. So maybe next class, so I'll stop here then. The next class, we will see examples of, or applications rather, of these two simplifications. Okay, if you remember, even in the Brachistochrone problem, I wrote once as one way of writing was d by dt of something I wrote, right? And said that, oh, that's what it would be. So we'll go back to those examples and we will see how these simplifications occur. And also we'll see some particular set of examples. Okay. So I think I'll stop here and pause for questions.
So can you give a quick example where the Lagrangian has explicit time dependence?
Oh yeah. wait. Let's do something. So you want Lagrangian, right? So let's write. Yeah. Arbitrary function of time. Here is an example. Another example would be, instead of mass, I can have something which will depend on time. So this is L1, L2 of Q dot T. I'm just playing around with Newton's thing, but now I've changed things, right? I'm saying that there's a time-dependent kind of mass-like parameter. So these are all examples.
Sir, from the second derivative of functionals, is it possible to determine whether the functional is a maximum or minimum of?
Yes. So in Newton's examples, I mean, I would suggest you go back and do the case for Newton's laws and see if you get, remember we know the stability conditions, it reduces to that in terms of the potential V. So see if that shows up. Okay. Does it mean we can't find a Hamiltonian if Lagrangian is explicitly dependent on time? No, we can. We'll get a time-dependent Hamiltonian. Energy just won't be a constant of motion. I mean, it looks very complicated, but actually, no, that's not true. Sometimes we pump energy into the system, right? Physically, in something, like when you're sitting in a swing, right? You start off with nothing. And then you start pumping with your legs, right? You are feeding energy into the swing, right? And then the amplitude starts increasing, etc. Obviously, here's an example where, things are time dependent, right? I mean, it depends on your pumping, right? So this L1, you will realize that L1, I think dL by dt will be some f of t, right? So yeah. So that's f of t will be some external force, driving force. Okay. So, any other questions? Yeah.
Sir, we accept the action principle like the Newton's law to find the...
Yeah. I mean, you never question Newton's laws, you never question this also, right? So, but the proof of the pudding is you're trying to, in a real system, you're trying to model some system, right? And you want to ask, does this, can we find an action functional which will reproduce the experimental data which we get? Only that's where the real money is. It's not a question of cooking up just some random action. You got to match with something, with some system you're trying to model. Okay, so that's where the thing is. And the great thing about the Lagrangian or the action principle is that it gives you a larger class of problems. And like I told you even last lecture, that it's a surprise that it works so well for so many classes. That remains a mystery. Okay. Yeah. So action principle is not. I mean, we just accept it. Okay. And this whole setup here is also Feynman's version of quantum mechanics actually looks at this and says that you have to, in some sense, all paths will contribute with some weight, and that weight is determined by the action. So, and the most probable one is what is the classical trajectory. So this is one whole story of the so-called Feynman path integral story, which fits into this. So at some point I might mention it, but this is not a course in quantum mechanics. So let me just stop recording. You can ask questions still.